Welcome to this channel. In this video, we are going to discuss AC load line in bipolar junction transistor. This is in connection with biasing circuit. I have seen that on YouTube, few professors are discussing like that. This AC load line and DC load line, they are essentially same, and they are considering that when inputs and outputs are connected, then it will be called as AC load line, and if input and output signals are not there, then the same thing will be considered as DC load line. But this is not correct. In this video, we are going to discuss this thing in detail. AC load line and DC load line, they will differ significantly. Especially their slopes are different, their purpose are different. Okay, let us start. First, we will consider one complete amplifier circuit. So this circuit we discussed in detail in the last video. While we have discussed the DC load line, again we will repeat the same thing, but very quickly. So you can understand this block, this total circuit. This is one major element. Okay, this is the transistors, collector, base, emitter. It is a NPN transistors. These transistors can amplify the signal, and this one is the input signal applied, and this is the output signal side. This V0 is the output signal, AC signal, and rest part RB, RC, CB, CC, these are considered to get the biasing circuit and coupling one. This CB and CC are called coupling or DC blocking capacitor. So here you can see that this amplifier contains one main element, that is the transistors, and if transistor is in active region, then only it can amplify. So we have to make sure that the transistors will be in active region. So for that, we'll do some DC analysis. We'll fix up our Q point or quiescent point. But remember that that is not sufficient all, because we want that this AC signal should be amplified by these transistors. Means at the output end, we should get the similar to AC signal, similar things, but amplitude is more. So V0 by Vs would be constant, but that value should be larger than 1. That we are interested. So V0 should be similar to AC signal, means same shape. It should not be distorted, means some part of Vs should not be truncated. Okay, meaning is that what I am saying, that once we will add the AC signal, the transistor should remain in active region. It should not go towards saturation region or cutoff region. In that case, the signal will be truncated. Okay, so we need to make sure that whenever we are going to add one AC input signal, the transistor will remain in active region. Okay, so once we will fix up our Q point using DC analysis, it is not sufficient. Okay, so we'll discuss this thing in detail here, and from there we'll get the AC analysis and AC load line. Okay, now to understand first DC analysis, this is required, otherwise you won't understand the AC load line. So first we will start with DC load line. So that I have discussed my last video, but very quickly I'll recap here. Okay, now for DC analysis, we should remove all the AC input and AC output. Okay, this side I should remove it. Okay, I want to go for only DC analysis, only DC signal, and this is our DC signal VCC that is connected. So this input side part I have removed. Similarly, I am going to remove this output side part, this one. So this one is left, and this is for biasing circuit. This circuit is called fixed bias circuit. We can have better biasing circuit, that is called potential divider self bias circuit, that will be discussed later, but we will work with this simple fixed bias circuit. So here we have resistance RB connected to the base side to this VCC, and from VCC through RC this collector is connected, right? Now we have analyzed this circuit. To analyze this one, we should have these two characteristics curve. One is input side characteristics and other one is output side characteristics for the BJT. Okay, and you can understand that in the BJT we have this kind of current flow. This is the base current, capital IB I am writing. This is the total current IC, and this is the emitter current IE. Essentially this IB plus IC will be equals to IE, and potential between base and emitter is VBE, that is in input side. So input side is base emitter is considered as input side and collector emitter is considered as output side. Okay, now based on this thing we can have different kind of amplifications. Okay, different kind of mode, common emitter, common collector, common base, that will be considered later. But remember that input side and output side would remain same. So either base or emitter, these two could be on input, any one. Okay, either base terminal or emitter terminal, we can apply AC input signal. Similarly, we can take output either from collector or emitter. We cannot take output from base. Okay, be careful. So if any one is common in between, suppose if emitter is common between input and output, then it is called common emitter mode. If collector is common in between input side and output side, then it will be considered as common collector. Similarly, if base is common in between input and output side, then it will be considered as common base. So those will be discussed in detail later. For time being, we want to understand DC analysis. So here what we have done this thing, that we have considered input characteristics. So input characteristics and output characteristics, these two will get with respect to this VBE and IB. This is for input side. Okay, similarly VCE and IC, this relation and this relation, these two were for these basic transistors, so that should be given to us. Okay, and you can see here that this IB and VBE, basically this is a diode configuration, PN diode, so its relation is nothing but a diode curve. Okay, and but this side, this output side characteristics IC versus VCE, will get a collection of curves for different values for IB. Okay, so this is the total thing we discussed last time. We'll just discuss briefly what is this and what is the load line. So from input side, this curve, this is the PN diode curve, exponentially growing. Okay, and from input side we'll get a equation, this KVL equation. This VCC equals to drop across RB plus VBE. So drop across RB is IB into RB plus VBE. So this is the input side equation. So this is the equation, straight line equation. We can plot it, and this curve, PN diode curve, and this one, this cross point, will get the solution, exactly the operating point. This I'll call it IBQ, and this is I'll call it IBEQ. Okay, normally we'll consider that VBEQ is around 0.7 volt, and based on this thing we can find IB current easily, because VCC minus VBEQ upon RB will be your IBQ. So that we can find quickly. In that case we can ignore this plot. We are considering that it is almost vertical here. Okay, so that is a different thing. Then the output characteristics curve, we have considered the VCE versus IC. We are getting a collection of curves for different values of IB. You can see. Okay, so once IB is fixed, IBQ, so we'll choose that corresponding curve here. So this is the corresponding curve, this blue one, for certain IBQ. Now again in output side we'll find one equation based on KVL. This supply voltage is VCC, drop across RC plus potential across VCE, across the collector and emitter, that is your VCE. So total supply voltage VCC equals to this drop across RC is IC times RC plus VCE. Okay, so this supply voltage equals to this addition of these two. So this is nothing but DC load line, and here you can note that this point will be on VCC. This is the VCC point, because when IC equals to 0, VCE equals to VCC. So it will cut the VCE axis at VCC point. Similarly, we can get this point. What this point? When VCE equals to 0, we'll put it, and IC equals to VCC by RC. So this point is VCC by RC. If I join these two, I will get a straight line, and that straight line is DC load line, and slope for this DC load line is 1 upon RC and negative sign. Okay, this negative sign implies that it is decreasing function, and its magnitude depends on this RC, 1 upon RC. If RC is large, its slope is small. If RC is small, then 1 upon RC is large, means slope is large, means more vertical kind of things. Okay, so more sharp, kind of sharp falling. Okay, so this is the Q point, and at this Q point, so here it will cut to this IBQ for this line for IBQ, and this is DC load line. This cos point is Q point, quiescent point. This is the stable operating point we are considering. This is your ICQ. This is this position, this line is called VCEQ. So this height is ICQ, and this length is VCEQ. Okay, in the previous lecture, then we tried to understand what is the amplification. Okay, how this BJT will amplify this thing, and for that we have considered only DC load line, but again we have said that it is better to use AC load line. Why? Because, so this is the thing, whenever we will add one AC input with this block, the DC, only DC load line, DC circuit, and we will connect one AC circuit, AC component, here load, okay, through CCC, CC, the RL is connected. So in that case, what is happening? So when some voltage is applied, so this voltage is going to differ, okay, we're going to change over this VBEQ. So because of that, the base current will vary. So we can expect that when input voltage is more positive, base current will be more compared to IBQ. So it is increasing, and when VI is negative, that time this VBE is reducing. As a result, this base current is reducing compared to IBQ. So it is varying. So this variation will call it small IB. So total base current I can consider as IBQ, the DC one, plus this small one, small IB. This is a total IB. Okay, now the reflection on the right hand side. So based on this IB, we know that, okay, this IC is related to IB by simple relation IC equals to beta IB. In that way also we can say that IC will be beta times of IB. So we are going to get a similar plot, but beta times of that. So it will now vary with respect to ICQ. Okay, but this height will be beta times larger than compared to this IB. Okay, so small IC we can expect that it will be beta times of small IB. That's fine. Now to get the idea about VCE, we have considered same DC line, and over this how IC is varying. Then we have considered corresponding, when IC is peak here, that time it will cut this point. Okay, this is a corresponding point, and we are considering that VCE is varying like this. It is coming here, and when IC is going toward negative side, that corresponding point is here, and that time VCE is going to this side. Okay, and that we have discussed with respect to DC load line, but this is not correct. Okay, this is not exactly correct. I said that we need to use AC load line, because that time that this slope will not remain same. Okay, so this RL will have some impact on this circuit, that we need to understand. So how AC signal will vary. Okay, so for that we need to consider all the input and output elements carefully. Okay, let us consider that thing in detailed way. So this is our circuit. Okay, I have included AC part, input signal, and this is the output signal taken through RL and capacitor CC, right? So here you know that total VBE will be combination of VBEQ plus VIT. So whenever I will add the VI, that will disturb your previous Q point. Okay, so now total voltage VBE will be VBEQ plus VIT. Similarly, this total IB will be IBQ plus small IB. Similarly, this IC, total IC is ICQ plus small IC. This is, and VCE is again VCEQ plus small VCE. Essentially, these are all DC component for Q points, okay, at DC operating point, and these are for AC signal. Whenever AC signal VIT is applied, we will be getting small IB, small IC, and small VCE. These are the AC components we will be getting in the circuit. Okay, and these are the total current or voltage, left hand side, right? Now we want to understand only AC analysis, means we want to get the relation between or among this IB, IC and VCE. This is the objective. So what we will do, we will remove first DC sources, because you can see here this total things, total voltage or current, it's a combination of DC value at Q point plus this AC. So it's one kind of superposition. So if I remove this DC component, if we work with only AC component, it is fine for us. Okay, so for that purpose, we will first remove the DC sources. We will work with only AC components. Now to remove the DC means what? The source is a DC, main DC part, DC source, VCC. So we need to remove this one. We should make it 0. First we will make this DC component 0. Okay, so if this is made 0, it is grounded, then what will happen? So now we'll start with this transistors. This is a major element, base, collector, emitter. Now we can see that this RB is connected to the base. Earlier it was connected to VCC. Now VCC is not there. We have removed it. So essentially it is grounded. So RB is one end is grounded and other end is connected to B. So I can say that from B point through RB and it is grounded now. Can I write in this way? Because you can see this point and this point same. Then it is actually connected to ground now. So that I have shown here. From this point through RB, it is grounded. Okay, because VCC is not there. Right, this is the equivalent circuit. Remember, this is the equivalent circuit for AC analysis only. This is not actual one. We want to remove the DC component, just we want to study AC components. For that purpose, we want to use this kind of simplified circuit. Okay. Similarly, the output side, what is happening? Earlier, this through RC, it was connected to VCC. So same thing we can do here. From C through RC, it will be grounded like this, because it was connected to VCC earlier. Now it is grounded. It is grounded here. Now what I'll do? So these components, input side and output side, we should connect. But here we will take one simple assumption. What I will do? This CB and CC are coupling capacitor. We are considering that for mid-band operation, medium frequency or higher frequencies, what is happening? They will contribute very small impedance. Okay. For mid-band, I am considering that whatever impedance they will offer, that magnitude is very small, negligibly small. So we can consider this thing as short circuit. As the impedance is small, it could be considered as short circuit. But this is not true for very low frequency signal. Okay. So if you use very low frequency signal, so CB and CC will contribute. That time we can't ignore. But we want to understand the AC analysis for mid-band and high frequency right now. Okay. And those low frequency component will be discussed later in some video. Right. So what I am doing essentially, CB and CC are sorted. So these two are sorted. Okay, then Vi is connected and RL is connected. So what I will get? This is sorted, then Vi is connected here, and this is sorted, CC is sorted, and RL is connected to ground. So this is now complete. This is our AC signal model. Okay, simplified thing. Okay, we need to analyze this one. Okay, now this RC and RL, how they are connected? They are connected in parallel. Okay, now this circuit, you can see that this current, I'll call it small ib, this current I'll call it small ic, and this I can call small ie. Okay, and this potential is VBE, small VBE, and this potential collector and emitter small VCE. All are AC components. Okay, now we need to analyze with respect to these parameters. Okay, now we need to simplify it further. So what I'll do, as I said that RC and RL, they are connected parallelly, so I can combine these two together. So parallel combination of RC and RL will be RC into RL upon RC plus RL, and that value is always lesser than the lowest of these two, and that I'll call it RL prime. So RL prime will be RC parallel RL, so single resistance I am considering, that is RC RL upon RC plus RL. Now we need to understand this circuit. Okay, so for that we can remove this part, we will focus on these things. So I'll focus on this circuit only. Okay, so how to do that one? And especially we want the output side characteristics. So input side characteristics I am not discussing right now, because we may get the variation in VBE. Because of that we will get the variation in IB. That will be discussed later. Right now we want to concentrate on output side, small IC and small VC. Can I get one KVL equation in this loop? This is grounded, this is grounded. Okay, so some potential drop across this one, and some potential across VCE is small VCE. And I have assumed that the collector current is small IC, it is flowing through this side, means from this to this side. Okay, so I can expect some potential drop here. This is plus, this is minus, and that value will be IC, small IC times RL dash, plus this potential VCE total. So there is no source connected here in this loop. So total addition of these two voltage should be equals to 0. So we can get in KVL equation this IC times RL dash or RL prime plus small VCE will be equals to 0. Right? Now this is important, very important thing. Now we can correlate this thing with our previous circuit, total current IC and total VCE. Okay, then only we will feel better. No, so we understand this thing, that total current IC equals to ICQ plus small IC, and total VCE equals to VCEQ plus small VCE. Now we can replace this small IC and small VCE from here. Okay, so what is this? Small IC, we can write that total IC minus ICQ, because from this total, if I remove the DC component, I will get AC component. That's the idea. Total VCE, if I remove the DC component VCEQ, I will get small VCE. So that I replace here. So small IC is replaced by total IC minus ICQ. Small VCE is replaced by total VCE minus VCEQ. Okay, so if I replace this thing, I will get an equation. Now in this equation, note that this ICQ is constant, DC current. This VCEQ, constant, DC voltage across collector emitter. RL prime, it is also constant. So which one variable? IC and VCE. These two are variable and they are related, linearly related. So this is nothing but a equation of a straight line, considering this one x-axis, this one y-axis. So if I consider this is x-axis, this is y-axis, this will give you a straight line equation, and that I can call it AC load line. Okay, that's very simple. So that's the difference between DC load line and AC road line. Okay, now this is exactly this AC road line, and you can note here that it is also passing through the Q point, because if I replace IC by ICQ and VCE by VCEQ, this is a Q point, X comma Y, VCEQ comma ICQ. So VCE is replaced by VCEQ, IC is replaced by ICQ. At that point in this equation, you can see this part will become 0, this part will also become 0, means again it will remain 0, means it is satisfied. So this point will lie on this straight line, means this AC road line will also pass through the same Q point. This is most important concept. So both DC road line, AC road line, they are passing through Q point, right? Okay. Now we can simplify it in a better way. So this is your variation, this is the variable IC times RL prime, and this I will keep it on left side, VCE, but this one minus ICQ RL prime, that I can take in on right side, this one with plus sign, and this one as well, VCEQ. So this is my modified equation. Now this equation we can plot in that output characteristics curve, then we can visualize better. Okay, that we will try. So what I will do, I will consider same output characteristics curve, VCE, total VCE versus total IC. Okay, and you know that if VC is less than 0.2 volt, it is going towards saturation region, and this side is active region, and IB should be more something non-zero, then only it is active region. Okay. Now I will consider this circuit. This is your biasing circuit, simple biasing circuit. Okay, in the biasing circuit, first we know that we can get the DC road line, that quickly we will get it. So from this base current IBQ, we will fix up one line, this curve, this is corresponding to IBQ. Now from this output side, we are getting the DC road line equation. What is this? This is your VCC equals to IC times RC plus VCE. Okay, IC times RC plus VCE equals to VCC. So that we can plot it here, as I discussed. So if I plot this thing, so this x-axis it will cut to VCC, as I said. So when IC equals to 0, VC equals to VCC, this point, and to get one, I need to get one more point on this axis. That time I replace VC equals to 0. So what I will get, IC equals to VCC by RC. So this point. Now I will join these two. So this is your DC road line, and it will intersect with this line, blue line. So we will get this operating point Q. So in this operating point, this is your ICQ and this is your VCEQ. Okay, and what is the slope for this one? It is minus 1 upon RC. Note that this is RC, so minus 1 upon RC, because why? I can write IC equals to minus VCE by RC plus VCC by RC. So y equal to mx plus c. If you compare, the m will be minus 1 upon RC. So this is a slope, negative slope. Okay, its sharpness depends on the RC value, as I discussed. Okay, now I want to draw this AC road line again over this. As I said that this AC road line will again pass to the Q point. Okay, and its slope is 1 upon RL prime minus sign. Okay, so this is your AC road line. It is passing through Q point. That is the important thing. We want to draw it. So it will be like this. It will pass through again, but this time its slope is minus 1 upon RL prime. Now its slope is larger than this one. Why it is so? Because RL prime is essentially the parallel combination of RC and RL. It is RC RL upon RC plus RL. Obviously this combination is less than RC. Okay, so RL prime is less than RC, and if it is so, then 1 upon RL is reciprocal will be more than 1 upon RC. So this magnitude is more compared to its magnitude, but both are negative. Negative means decreasing. Its meaning is that AC road line, its slope is sharp, it decreasing rapidly compared to DC road line. Okay, because its magnitude is high and it is negative, that's how its slope is high, highly negative. Okay, so and you can note that this point will be what this point when IC equals to 0. So then VCE will be ICQ RL prime plus VCEQ, this point. So this is your VCEQ and this gap is ICQ into RL prime. And that we can show that this value is less than VCC. That's not difficult to show. Okay, because VCC, what is VCC? IC times RC plus VCE. Okay, now if I replace the Q point, ICQ RC plus VCEQ is also VCC. So VCEQ plus ICQ into RC, that is equal to VCC. But here ICQ into RL prime, earlier it was ICQ into RC, and already I said that RL prime is less than RC. So this term ICQ into RL prime should be less than ICQ times RC. That's how this value is lesser and positive. So total value, this value VCEQ plus ICQ RL prime is less than VCC. Hope you can understand. Similarly, you can prove that this point on this y-axis will be larger than VCC by RC. That you can try. Okay, I am leaving to you. Try to understand. Just consider this thing that RL prime is less than RC. That's all. Okay, so this is passing through this one. Now, what is the important thing? As we have got this AC road line, now everything, all the AC components should be discussed with respect to this AC road line, not DC road line. Okay. Now what is the meaning? Meaning is that now in this over time, if IC is varying, suppose earlier it was a constant ICQ. If DC is present, I will get only ICQ. Similarly, if DC is present, I will get only VCEQ. This I am plotting here. This is a VC. This is a y-axis. This is a T. This is a T. Okay. Now whenever input is applied, IC is varying. IC will vary over this. Okay. That I can show here. So this small IC is added over this ICQ. I will get total IC. Okay. And for that, we need to get corresponding VCE. So what will do when it is reaching to this peak value, that time this is the level. So it will cut here. So this corresponding thing we can find. Okay. Similarly, this corresponding will cut here. This corresponding I can put it here. Okay. So what will happen? This one. So this is the thing that in IC, when it is increasing, that time this value is okay. This point is moving from this to this side. So VCE is coming to this side. And when it is reducing, this is going to this side. Okay. So this plot, it should be with respect to this AC load line, not DC load line. Is it okay? This is very, very important thing. So what you can do, we can remove these things, DC load line for time being. We can work with only AC load line to get this AC variations. So essentially, if we want to compute amplification factor or other things, we need to consider only AC load line and its slope. Its slope will be -1 upon RL prime, not DC slope. DC slope will not be considered, okay, to find the amplification factors. Okay, so you can see that I can remove these things and I can get these variations. I hope you have understood what is the meaning of AC load line and how it will differ from DC load line. Okay, so we will discuss more things. So if you have enjoyed this video, you may just like this one, and if you have not subscribed this channel, you may subscribe this one. I will be discussing more things, concept, lots of other subjects we will be discussing in this channel. Keep watching. Thanks for watching.